This is Dr. D. Govardhan, Professor and Head of Department of Aeronautical Engineering, Ministry of Aeronautical Engineering, Hyderabad. Today the topic is moment of inertia, radius of gyration, polar moment of inertia, theories of moment of inertia. Moment of inertia is the geometrical characteristics of a cross section of a members. The strength and stiffness of bending members depends on moment of inertia of the cross section. The moment of inertia is also called second moment of inertia of a plane section about a given axis, depending on the sum of the product of obtained by multiplying each area by the square of the distance between the axes. The moment of inertia of a plane area. Now consider a plane now, which is divided into some number of segments, having each element is having area of cross sections A1, A2, A3 and so on, and it is kept under coordinate axis, that is x-axis and y-axis and so on. Let R1 is representing the position of center of gravity of A1 with respect to the y-axis, and A2 with R2 distance with respect to the y-axis, A3 and so on. Now, then the moment of inertia of all the elements, the sum of the moment of inertia of all the elements about the y-axis is equal to the moment of inertia of that entire cross section about the y-axis. That means the moment of inertia of the whole section, if it is represented by mi, it is equal to sum of the moment of inertia of all the elements about the y-axis or about the same axis, a1 r1 square plus a2 r2 square plus a3 r3 square. Simply it can be written as sigma of a r square now, where r is representing the center of gravity of that entire area about the reference axis, that is we have taken here y-axis. The units of moment of inertia generally depends upon the units of area as well as the length. Since the moment of inertia about any axis is representing the product of area multiplied by the square of the distance between the center of gravity to the reference axis, hence area is representing in if it is in meter square and length in meter, then the moment of inertia is represented as area multiplied by the square of the distance, it is equal to meter to the power of 4. Similarly, if the area is represented in mm square and the distance between the center of gravity to the reference line is represented as mm, then moment of inertia is represented in mm to the power of 4. Methods of moment of inertia. The moment of inertia of a plane area can be found out by using two methods. One is Rouse rules. The second one is by using integration method. The Rouse rule is generally used to find the moment of inertia of plane area, and which is having in the shape of regular objects such as square, rectangle, triangle, circle, semicircle and so on. Hence, this method is generally not preferable for the engineering applications, only it is having academic importance. The second method is integration method. In order to overcome the problems like earlier we have taken Rouse rule, it is only applicable to the regular figures. It is applicable to all the objects, including regular as well as the irregular objects, and hence it is preferable for determining moment of inertia in the field of science and technology. the moment of inertia by using Raoult's rules. All I told you, it is applicable to regular figures. Here regular figures means it may be the square or rectangle, triangle, circle and semicircle. According to the Raoult's rules, the moment of inertia of a rectangle is given by ARM multiplied by S by 3 now. Here I am taking, this is known as the x-axis now, it is the y-axis, and a plane which is in the form of rectangle is represented here. According to Raoult's rules, if a body is symmetrical about the 3 mutually perpendicular axes, because if you take this object, it is a perpendicular, it is now symmetrical about the x-axis now, vertical axis, horizontal axis, as well as the z-axis there now, which is a perpendicular to the plane of the area now. That is the 3 coordinates are there now, x coordinate, y coordinate and n. Here, since we are taking the object is symmetrical now, that is a regular figure. Hence, according to the Raoult's rules, the moment of inertia of about any one axis, which is a passing through its center of gravity, is given by moment of inertia is equal to ARM into S by 3 now, where A is representing the area of the plane now, or M is representing the mass of the plane area, if it is having uniform thickness. Multiply by S by 3 now, where S stands for the square of the sum of the squares of the 2 semi-axes other than the axis about which the moment of inertia is required to be found out. That is, here I am required just to find the moment of inertia of a rectangle about the z-axis now. That is, the semi-major axis here now, semi-axis are now. If B is representing the breadth of the object now, that semi is nothing but here B by 2. Similarly, D is representing now depth of the rectangle now. The semi depth is represented here now D by 2. Now, according to the Raoult's rules, the moment of inertia of rectangle is given by, it is the product of area or the mass into S, where S stands for the sum of the squares of the 2 semi-axes, that is B by 2 whole square plus D by 2 whole square. This about an axis which is a perpendicular to these two and passing through the center of gravity of the object now. S by 3 now, here this equation is only applicable for the determination of moment of inertia of a square or rectangle of a lamina or the plate which is having uniform thickness. Similarly, ARM, that is the area or the mass, multiplied by the S by 4, where S stands for the sum of the squares of the 2 semi-axes other than that axis about which the moment of inertia is required to find out, by 4, where this equation is applicable for determination of moment of inertia of circular as well as the elliptical lamina. The third one, it is applicable for the sphere now. It is given by ARM into S divided by 5 now. Here A is representing the area of the plane area. That is this equation, when you are substituting A values, area, the obtained value is known as the moment of inertia of an area now. If it is A is replaced by M, mass moment of inertia of a body, that is Mi is equal to, that moment of inertia is equal to, A is replaced with M and multiplied by S by N. N is equal to, it may be 3 or it may be 4 or it may be 5. If it is a 3, it is a stand for the square or rectangular. When you substitute divided by 3, it is applicable for square or rectangle. 4 circular or elliptical lamina. 5 stand for the spherical body. It is only applicable for academic purpose, but not for science and technology applications. The moment of inertia by using integrations. Here the moment of inertia about any axis, here now about the y-axis, is given by the area multiplied by the square of the distance between the center of gravity to the reference line, that is dA into x square now. Similarly, with respect to the x-axis given by dA multiplied by the square of the distance means y square now. That is y square dA is representing the moment of inertia of a plane area about the x-axis. This moment of inertia of plane area, it may be the regular or it may not be regular. For all bodies, generally the moment of inertia using integration method is applicable now. Here we are considering a figure, plane figure, which is having area is dA and having coordinates x and y with respect to the xy coordinate plane as shown in figure now. Now, according to the principle of moment of inertia, the moment of inertia of that small area dA, here which is represented here now, about the y-axis is given by dA into x square now. Similarly, the moment of inertia of the entire area is obtained by using this integration or sum of the elements of the moment of inertia possessed by the all the elements, which is equal to I is equal to sigma dA dot x square now. Similarly, Ix is equal to sigma dA into y square now. Now, moment of inertia, theorem of perpendicular axis. Now again I am taking the area, the elementary area dA, which is kept under xy coordinate plane, having coordinates xy as shown in figure. According to this figure, the moment of inertia possessed by that small element dA, because I am considering small element, elementary area here now, the moment of inertia of this area about the y-axis given by x square into dA now. Similarly, the moment of inertia of that same area about the x-axis given by, that is Ixx is equal to y square dA. Similarly, Iyy is equal to x square and dA now. The moment of inertia of the same area about an axis which is a perpendicular plane and passing through the intersection of x-axis and y-axis, that means here the origin. I am taking here now perpendicular to the plane like this now. Let R be the distance between the center of gravity of that elementary area from the origin. Then moment of inertia possessed with the element about the z-axis, that is which is the perpendicular to the x-axis and y-axis given by Izz is equal to r square into dA now. Now, according to the geometrical figure now, the distance is already represented as x now, and the distance is represented as y now. That is r square is equal to, we can put it as x square plus y square now. On substituting Izz equation now, that is Izz is equal to, we can written as now x square plus y square into dA or x square dA plus y square dA now. That means Izz is equal to, it can be written as Ixx plus Iyy1. Now, by using these equations, we can define the theorem of perpendicular axis applicable to moment of inertia as the moment of inertia of an area about an axis perpendicular to its plane. That is, we are taking z axis now. This Iz is called polar moment of inertia. That means the moment of inertia of an area about an axis perpendicular to its plane. It is called polar moment of inertia. About at any point O, is equal to the sum of the moment of inertia about any two mutually perpendicular axes passing through the same point O and lying in the same plane of area. That means, if y-axis is representing the moment of inertia of that plane area about the y-axis, Iy is representing moment of inertia of the plane area about the x-axis, then according to the theorem of perpendicular axis, Iz is equal to Ix plus Iyy. This equation is known as the theorem of perpendicular axis. So, it can be proved as now already I told Iz is equal to r square d square now, r square dA. The moment of inertia possessed by the entire area is given by sigma of r square dA. R square is equal to x square plus y square dA, already we written. Sigma is a common word, hence it can be written as sigma x square dA plus sigma y square dA. It is equal to Ix plus Iyy. This equation is known as equation representing theorem of perpendicular axis. Moment of inertia, theorem of parallel axis. The moment of inertia about any axis AB, here we are taking about any axis means AB, is equal to the sum of the moment of inertia about a parallel central axis and the product of area and the square of the distance between the two parallel axes. Let the area is there now representing here now. Let GG is representing the central axis. Central axis means the axis which is passing through the centroid of the given object or the plane area. Let us find the moment of inertia of that entire area about a line AB, which is parallel to the GG as shown in figure. According to the theorem of parallel axis, IAB is equal to the sum of the moment of inertia of the plane area about its central axis, that means GG, and area multiplied by the square of the distance between the parallel axis now. That is, the distance between the parallel axis is given by according to this figure, which is representing now. Hence, IAB is equal to IGG plus area multiplied by the square of the distance between the two parallel axes now. This is represented in the equation number 1, where IAB is representing the moment of inertia of that entire area about an axis represented here as AB. IGG is representing the moment of inertia of that entire area about its central axis and parallel to AB. A is representing the area of the entire figure and Y is representing the distance between the two parallel lines, that is AB and GG, here represented as YC now. Okay, just proof. Now we are considering in a plane figure having total area is equal to A. Let GG is representing the central axis, which is drawn parallel to AB, about which the moment of inertia of that entire area is to be determined. Let YC is representing the distance between GG and AB parallel lines. Now consider a small strip which is at a distance of y from the central axis as shown in figure, having area is equal to dA now. The moment of inertia of small segment dA about a line AB is represented by the product of area multiplied by the square of the distance between them now. That is IAB is equal to small area, assume D is equal to, we can take it as now, distance is equal to YC plus YE, this is the distance, into square of the distance multiplied by the area now. Then the moment of inertia of the entire area about a line AB is obtained by doing integration of all the elements, or the moment of inertia possessed by the all the elements with respect to the AB now. So it can be represented as now sigma of YC plus Y whole square into dA now, which is represented here now in this equation now. And expanding it, since it is in the form of A plus B whole square, Y square into 2YC plus YC square into dA. Sigma means here nothing but the moment of inertia possessed by the all the elements about a line AB now. Again, and expanding, it can be written as now sigma Y square dA plus 2y YC dA plus sigma of Y square dA now, where sigma Y square dA is representing the moment of inertia of that entire area about its centroidal axis now. Hence, it can be represented as now IGG now. The second term is there now 2YCA. 2 is a constant. YC is the distance between the two parallel lines. It is also constant. And the area is also constant now. And so, in the equation now, sigma of y dA by dA, since I am writing this equation like this now, 2 into YC, sigma of y dA, this 2 into YC is the constant now. So, the remaining terminology is equal to sigma y dA, it is there. And so, multiplying dividing by area, that is sigma dA into sigma dA is equal to area now. That is in the equation is a 2YC into A, it can be written as now sigma y dA divided by sigma dA now. This is representing the position of the strip with respect to the position of center of gravity of the strip with respect to the GG line. But according to our consideration now, the GG line, it is representing the central axis. That means it is passing through the centroid of the entire area now. That means the sigma y dA divided by sigma dA, that is representing the position of centroid with respect to central axis. That means it is equal to 0 according to the fundamental of center of gravity or centroid equations. Hence, the second term it is equal to 0 now. The remaining terms, sigma y square dA is there. YC is representing the distance between the two parallel lines remains constant. The integration of dA it is equal to the total area of the element. It is also constant now. So, substituting all the values in the above equations, we got to sigma y square dA is equal to AYC square. Hence, IAB is equal to, it can be written as now IGG plus AYC square now. That means the second term it is there now 2YC and YDA it is equal to the 0 now. So according to the principle of parallax theorem, the moment of inertia of a plane area about a line AB or any line is equal to the sum of the moment of inertia possessed by that entire area about the central axis, which is the parallel to AB, and area multiplied by the square of the distance between them. This is known as parallax theorem. Generally, parallax theorem is most important for engineering as well as the science applications, because we have to determine the moment of inertia possessed by the two rotating parts or elements of the machines about a required axis now. Now, polar moment of inertia. The polar moment of inertia is inertia possessed by that element about an axis which is a perpendicular to the plane, That means here dA is representing the given plane. It is kept under xy coordinate plane. The moment of inertia possessed by the element about an z-axis. Z-axis means nothing but here the axis which is a perpendicular to the plane is called polar moment of inertia. Okay, according to the theorem of perpendicularity theorem, the polar moment of inertia, that is the moment of inertia possessed by the about z-axis, is equal to sum of the moment of inertia possessed by that same area about the x-axis and y-axis. That means these two axes which are perpendicular to each other and passing through the intersection of z-axis. So the moment of inertia about the z-axis, let us consider an element dA, which is at a distance of x and y from the y-axis and x-axis as shown in figure, and R is representing the position of that area about the intersection of these two lines, that O. So according to the principle now, IZZ is equal to sigma R square dA now, where R square is equal to x square plus y square, hence sigma x square plus y square dA, which is equal to Ix plus Iyy. This theorem is known as perpendicularity theorem, where Iz stands for the moment of inertia of that plane area about an axis which is perpendicular to its plane. Sometimes it is also called polar moment of inertia. The polar moment of inertia is equal to sum of the moment of inertia possessed by the area about two perpendicular axes, x-axis and y-axis, and passing through the intersection of z-axis. That is which is perpendicular to the plane now. Radius of gyrations now. Radius of gyrations mathematically defined by using the relations now. Here we are having the moment of inertia possessed by that any element is given by I is equal to m x square, or we can call it now a x square now, where x is representing the position of the centroid with respect to the reference line now. If the assume that entire area, if it is sometimes irregular now, assume that entire area is assumed to be concentrated at point now. At which point it is concentrated? It is concentrated always at its center of gravity only now, or centroid of the plane area. If it is at a distance of k from the reference line, that is the axis now, then the moment of inertia possessed by that entire area about an axis given by area multiplied by the square of the distance between them now. That means I is equal to, we can take it as area multiplied by the square of the distance. Assume that distance is not with respect to the x-axis or y-axis, with respect to some axis we are taking the reference line. Hence, I am taking this as k now. That is I is equal to a into k square now. Then k is equal to, it can be written as now, k is equal to, according to this relation now, I divided by a under root now. Where k is representing the distance between the reference line to the center of the given segment or given plane, it is that the entire area is assumed to be concentrated. Then that k is called here radius of gyrations, and I is here represented moment of inertia of that entire area about an x-axis. Area A is representing the area of the cross section. Then next, from the above relations, the term radius of gyrations is represented as the distance between the reference line to the point at which that entire area is assumed to be concentrated. That is, the completed area is spaced and kept as a steep negligible width now. That is nothing but concentrated, such that there is no change in moment of inertia later now. That is, here k is the distance between the reference line to the point at which that entire area assumed to be spaced, that is concentrated, or in other words, center of gravity at the center now. Now, which is equal to, according to the mathematical distance, it is the square root of, that is k is equal to under root of I by k now. That is, where I is nothing but stand for the moment of inertia, A stand for that area of the plane now. It is the distance between the reference line to the point at which that area of entire plane assumed to be concentrated. This point is called radius of gyrations. These equations are most useful for determination of the momentum possessed by that element as well as the energy possessed by the element when it is in rotations, motions. And the moment of inertia plays key role for engineering as well as the science applications, as mass which is playing when the body is in plane motions. Here, if I take the equations now, the kinetic energy possessed by the mass when it is a linear motions is given by 1 by 2 mv square now. But when the mass is in rotation motions, it can be written as I omega square now. That is, the moment of inertia is playing as the role of mass when the body is in rotary motions. This is the important of the moment of inertia and most useful particularly for the engineering applications. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.